Hello, I'm Bernard Dern. I'm the Editor-in-Chief of Developmental Medicine and Child Neurology. For the January 2017 issue, I wrote an editorial entitled Gap Junctions in Epilepsy, for Better or Worse. And I'd like to expand on this in a conversation with my friend Roger Traub, who's an expert. Hello, Roger.
Hello.
Good to have you here. So,
you.
will you tell a few words about yourself and where you are?
So I studied mathematics and then medicine and trained in neurology at Columbia Presbyterian in New York. And I've been making models of nerve cells and neuronal networks since the 1970s with a special interest in epilepsy.
And how did you come about the idea of gap junctions in epilepsy at all?
That began when I was spending 4 years in England, and Andreas Dragoon was visiting from Germany, and he made an accidental discovery. So the background to this is there's a phenomenon well known in the hippocampus called sharp wave ripples, which are supposed to be important in memory consolidation. And there was a lot of controversy about the mechanism. It appeared that the sharp waves had some resemblance to epileptic sharp waves, but weren't as big, weren't as synchronized. Mm-hmm. But the ripple, which was a very fast 200 hertz oscillation, was completely mysterious.
It was mysterious because 200 hertz is so fast.
Yes.
Mm-hmm.
And what Andreas discovered quite by accident was that he could observe the ripples in a brain slice without the sharp wave. So they were dissociable phenomena.
Right.
And he then discovered that the ripples would occur even when chemical synaptic transmission was completely suppressed. But on the other hand,
excitatory influence as well as inhibitory?
Both excitatory and inhibitory. So he would bathe the slice in a low calcium medium and show that all evoked synaptic responses were suppressed. But instead of blocking the ripples actually were enhanced. So he then showed that various gap junction blockers, none of which are particularly wonderful in that they have side effects, so to speak, but each gap junction blocker has its own side effects, and the side effects are all different. And every gap junction blocker would suppress these ripples.
So the idea was that it could be gap junctions because chemical synapses did not seem to play a role.
Yes.
And we know that gap junctions are present very early in maturation, but it probably came as a surprise to see a potential role for gap junctions at a later stage of maturation.
No. Well, yes and no. So it was known that there were many gap junctions between interneurons, that is, inhibitory cells, late in development, even into the adult. It wasn't so clear that gap junctions continued to exist between adult principal cells. But there was some evidence. And after these experiments of Dragoon et al., the issue was revisited, and it was discovered that, in fact, principal cells are what's called electrically coupled, which is presumably by gap junctions. And there was also suggestions before this that gap junctions might exist between principal cells because of a phenomenon called dye coupling. So you inject a fluorescent dye into one neuron, and you wait, and then it ends up filling other neurons. And that suggests that there's some pathway between the cells, not a chemical synapse, which would not pass a fluorescent dye. A gap junction is like a tunnel, so it can pass dyes if they're not too big. The molecules aren't too big.
These oscillations, can they be measured in vivo in patients?
Let me go back to the in vitro experiments for a bit. The question was, let us suppose that the oscillations come about because of gap junctions. How would that happen? And that led to developing a model which depended on a simple idea, which was each cell should be coupled electrically to just a few other cells, but the coupling had to be very strong so that action potentials could pass from one cell to another. So that was then confirmed, and this became a plausible model of high-frequency oscillations. Then the next question was, in what circumstances besides sharp wave ripples do you actually see them? And it turns out that it was already known that focal epileptic seizures could begin with a run of very fast oscillations.
Right. And
that's actually part of the background of how we met in London with Torsten Baldeveg's recordings of a series of children with cortical dysplasias. And all of these children, their seizures began with this run of very fast oscillations.
Yeah, which you can best see in electrocorticography because of the amplitude. But then once you recognize it, and if you have the right tools, you can actually see them on EEG.
Well, they've been seen in EEG in babies. It's hard to see them in EEG in adults, I guess.
Yep.
That's the frequency.
And then you said that gap junctions blockers were used. How far are we in trying to use gap junction blockers in the treatment of epilepsy?
Not very far. There's a drug that's used as an adjunct treatment, which is a carbonic anhydrase inhibitor. And it's, as I understand, not a particularly good anticonvulsant drug, but it is used, and it would have the effect of producing relative acidification. Oh,
right. So the way is not directly through acting, so a drug acting on the gap junction, but changing pH.
Yes. All right. So I neglected to say that. So going back to the original Dragoon observations and repeated many times, these kinds of oscillations are very pH sensitive, and they're enhanced by alkaline pH. And interestingly, the common gap junction protein in the brain is called connexin 36.
Yep.
Connexin 36 actually closes with alkalinization. And that suggests that the gap junction protein is not the usual one, but it's one of the other less common ones. And in fact, there's very strong suggestive evidence that it's connexin 45. So there was recently a study. It was a screen of all the messenger RNAs expressed in principal neurons in the hippocampus, and the connexin 45 mRNA is very prevalent. So that is the likelihood, not proven, and it turns out that connexin actually does open with alkaline pH.
This body of research might change the outlook to management of epilepsy very dramatically. Which are the following research steps that you foresee, Roger?
Well, what I can tell you what I would like to foresee. As far as I understand, it's technically feasible to combine pH measurements in the human brain with electrocorticography. This is something that's technically possible, but as far as I'm aware, has not been done. The crucial clinical observations would be to measure electrical waveforms simultaneously with pH in the cortex. And the prediction is that the first signal that you see prior to the seizure is a change in pH. And then you would see the fast oscillations, and then you would see the seizures. That is the kind of research that needs to be done, but as far as I'm aware, has not been done. If that's the case, then that would very much strengthen the argument to look for drug therapies that might affect brain pH or gap junctions in other ways.
So this podcast may also be an invitation to the research community involved in epilepsy research, and I hope we can continue this conversation much more widely with all those partners.
Yes, I certainly hope so. I think this is something that could make a real difference, It's based solidly in basic science and in clinical observation, but obviously we need more data.
Mm-hmm.
But the thing is, it's not kind of abstract data. It's the kind of data that really could be collected if there was a will to do it.
Okay, I think you and I together probably know the right people. So let's use this to get to them. Thank you so much, Roger.
Thank you.
And take care. Bye-bye.